All right, everyone, and welcome to this session where I'm going to talk about a proactive approach to resilience in modern applications. Before I jump into it, I want to get a sense of the audience. So, how many of you are SREs today? That's quite a few. All right, cool. How many are using serverless today? All right, that's also quite a few. Cool. So, I want to talk about how these modern types of applications give us a few different challenges than perhaps more traditional architecture. Why the traditional way of looking at resilience isn't really enough in many cases, but then also show you some of the things we're doing at AWS to hopefully help with this. And don't worry, it's not a product pitch. I know it says AWS huge on my chest, but I am going to use AWS services, but we're all friends here, so don't worry. My name is Gunnar. I am a developer advocate with AWS, clearly. And yeah, let's get into it. I think many of you might have seen this. If you don't know, this is Werner Vogels, the CTO of Amazon. And this is his, I think, most famous quote, that everything fails all the time. And I think this is particularly relevant for modern application. And the key insight with this isn't that we should be pessimistic about failures. I think it is that we should be realistic and proactive. Because when we accept the failures are inevitable, we can start designing systems that embrace failure as a natural occurrence, something that just keeps happening in our systems. And we can then perhaps move from being reactive to more proactive when it comes to resilience. And also build confidence, both in the systems and in the way we as teams work in terms of these things. So it's really a mindset thing. I'm talking about modern applications. So just once again, to set the stage a bit, this is a definition of what I see as a modern application, that it's a collection of cloud-native services that are designed to be secure, resilient, and easily scaled to then in the end deliver business value. So just to break that down with collection of services, I mean that we're not dealing with monolithic applications or systems these days. And cloud native, it tells us that it's built for the cloud, in the cloud. And then secure and resilient, those shouldn't be afterthoughts. It's something that we are designing the system to be from the start. And then easily scales, that means both technically that it should be able to scale, but then operationally, so that the system should be able to grow and our organization should be able to handle that. And I think most importantly, all of it just ties back to delivering business value. That's basically why most of us are in business. Yeah. So modern applications, and so look at some of the characteristics that make these applications a bit different from traditional ones. I think most modern applications have evolved from the traditional architectures. And there are four key characteristics that I like to point to when it comes to this. One is that the applications are distributed by default. It's just a way that we build them. Like I said, it's not monolithic applications anymore. They naturally span a bunch of different services usually. They can span across availability zones, across regions, different parts of the world. So they are distributed by default. And secondly, we've moved quite a lot towards event-driven architecture. So we have systems that react to different types of events. And they communicate through messages between these different parts in that distributed system. And that gives us a lot of flexibility and it gives us scalability, but it means that we need to make sure that we can keep up with state management and how these events are handled. And then these types of systems, they rely heavily on managed services. So that means that we can focus on the business logic, the thing that makes money in the end, but it also means that we rely on that someone else, the cloud provider usually, they deliver a service that works for us. And we can't really touch all of the parts in that system. And then finally, most modern applications, they run on ephemeral compute resources, things that come and go, scale automatically and dynamically. So there's no guarantee of persistent state, and we need to handle different types of challenges like cold starts and initialization, so on. And this brings then a few challenges. So first off, a lot of the deployment units are small and they're getting smaller. So instead of deploying one large application, we are deploying many small independent services. And each of these become their own potential failure point within the architecture. And usually all of these different services and parts within the system, they have their own configuration, and that's timeouts, permissions, retry policies, and so on. And they all need to be set correctly. And any type of misconfiguration in any of those parts can cause issues that ripple through our system. And then different services, they fail in different ways. If you have a database throttling error, that can look very different from an error within, say, AWS Lambda timeouts or API gateway quotas being hit. And each of these failure modes, they need to have their own detection and strategy for being handled. And then finally, with these managed services, like I said, we are letting go of part of the control to the cloud provider, the one delivering the service to us, meaning that we don't have visibility about what's happening under the hood. We can't touch all of those parts. And I know many of us probably in this room, we love getting down to the nitty gritty, and we love, I don't know, I might get kicked out now, but some love to run your own Kubernetes clusters, and that's fine. Fully managed service, yeah, they don't allow you to do those things. So to be able to address these types of challenges, we need to have a very systematic way of thinking about these failures. At AWS, we usually talk about this framework with the different failures, where we're talking about single points of failure, excessive load failures, excessive latency, misconfigurations and bugs, and shared fate. So most of the failures that we see, they fall into one of these different categories. So we need to be able to then handle these types of failures within our modern applications. So I asked you a couple of questions initially. Given the audience, I think most of you know what chaos engineering is. Chaos engineering is a way to tackle many of these challenges, but chaos engineering has its own challenges when it comes to modern applications. This is the definition of chaos engineering, the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. This is from the book Chaos Engineering by Case Rosenthal and Nora Jones. And just to be clear, there are other great books about chaos engineering. So, what? Yeah, I was waiting for that. Please check out both of these books if you haven't already. But chaos engineering is a continuous way of looking into your applications and trying to make it more resilient to failure. It is a scientific method that we're using, where we're starting out with a steady state, then we're creating these hypotheses around the system, running different types of experiments to verify that hypothesis, and then hopefully in the end be able to learn something that makes us be able to improve the system. And we do this as a way then to, in the end, build a system that's more resilient to failure. But once again, failures will happen in our system. It's just a matter of being able to understand what those, many cases, unknowns within our systems are. When we create chaos engineering experiments, there are different types of categories that we usually do. It can be around hardware failures, for instance, simulating, but actually running it, a hardware failure for our systems. Or it could be software failures, like malformed responses, different types of things that happen within our code or within whatever the application we're running is. It could be events that aren't reaching where they should go, or we can have traffic spikes or issues with scaling. And any type of event really that could then disrupt that steady state in our application. But then, once again, going back to the way modern applications work, where we don't have access to that underlying infrastructure, means that it's a bit trickier. We can't just plug the cable out of a server, or we can't stop an instance or a specific process to run on a specific server. Instead, we need to usually find different ways of doing this. And when it comes to serverless and these types of modern applications, they have very specific failure modes. For instance, if you've ever done something with AWS Lambda or similar services, something that often comes up is the issue with cold starts. that the first time a function is invoked, it takes a bit longer because it needs to initialize that function. And that can have an effect on the system. But if you have a system that is continuously running, usually you don't notice that. But what happens those few times that you have cold starts? That's something that's worth exploring. And also in terms of timeouts, issues you might have in your system if there are timeouts between these different moving parts within the system. What happens then? And it could be that your system is scaling more than perhaps you anticipated. So you might run into concurrency limits or throttling. Maybe your modern application needs to talk to a legacy system downstream. That system can keep up with how the system is scaling. So that's another unknown to be able to look out for. And it can be anything to for instance, service quotas, limits on the different services you have in specific regions, in specific accounts, and so on. What happens if that happens within your system? And when it comes to serverless and modern applications, there are a bunch of different patterns that we use to try to make the system more resilient to these types of failures. For instance, we're implementing circuit breakers for our APIs. So if that downstream service doesn't work, we can have a breaker to then stop trying to hammer the legacy system, for instance, or the relational database or whatever it might be. We're using dead letter queues for messages that aren't being processed, so we can then reprocess and redrive those messages. Using idempotency, so we're not transferring money twice to the same account. Instead, we make sure that we can only do it once. We have strategies for retries in place. Monitoring observability, obviously important. And then once again, timeout. Knowing what timeout configuration to have in these different systems. So the point here is that these modern applications, yes, they are easier because we don't have to perhaps do as much heavy lifting, but they introduce some other failures or failure modes and other unknowns for us that we need to be aware of. Because sooner or later, everything will fail, like Werner said. So now I want to show you a couple of examples of the things we at AWS tend to tell our customers to do, things you can do to hopefully make your life a bit easier. And I'm going to do that by showing a simple application. This is the easiest serverless application we can have. This could be its own application, an API that's being called by someone, or it could be just one of the services or microservices within a huge application that you're running. This could be connected to a front-end application, some sort of React application that's fetching data from it. Doesn't really matter, but this is a typical simple serverless application. So the first thing we try to get customers to do is to compare your application, whatever you're building, to our well-architected framework. The well-architected framework contains loads of information about different ways how to build and operate things on AWS. And in the past, that's been checkbox, checklist type operation where you have to yourself go through a bunch of questions and try to see if that compares well to the framework. A couple of years ago, we released a service called AWS Resilience Hub, which is meant to help you with this. So a more proactive approach to how to make sure that your application is resilient to failure. So I'm going to quickly walk you through how we use that. So Resilience Hub has two parts, resilience management and resilience testing. We'll start out with resilience management. And what I'm going to do is just add my application to Resilience Hub. So giving it a name, I then select how the application is managed. That could be, for instance, a CloudFormation stack or a resource group. I'm just going to select my stack in this case. It could be a Kubernetes cluster as well. I can then assign a resilience policy. That means my RTO and RPO targets. So I can set those myself or use one of the templates that are available. Switch back, use one of the preset ones. Then I have to give it permissions, of course. So I have a role that has access. It can read my information about this service. And then I can set this up to do a schedule assessment. So it runs every day in this case. It can also notify me if there are changes, drift in the application. All right, so now I've added my application. Then I'm going to publish this version. So now the way my application looks is the published version. And now I can create an assessment of this. So run that. There we go. Now we have a report that we can then look at. So now it's compared my application to some of those best practices from the well-architected framework. And we can see that lots of green, looking good, but we actually have something that says that the application isn't compliant. So then we can look at these findings and see there is an issue with our DynamoDB table in this case. It is unrecoverable because we don't have point-in-time recovery or backup plan in place for our DynamoDB table. Means that if something were to happen, we wouldn't be able to roll back within our RTO or RPO time. So then it gives us suggestions of how to improve this. It shows us these are the options we have, and it also gives us a CloudFormation template, basically, to be able to actually just get this done as well, make these changes for us. So this is then based on, like I said, the well-architected framework and how that tells us to do things. It would also give us some operational recommendations. For instance, it's checking, do we have alarms set up for the specific parts of the application? If we don't, it will tell us these are the alarms we suggest that you have in place and how you can set those up. It also gives us some suggestions of standard operating procedures. So people who are SREs, who have to perhaps wake up in the middle of the night, they know what to do to be able to restore things. So that's how Resilience Hub works from that resilience management standpoint. The other part of it is the chaos engineering part, resilience testing. And that's also within Resilience Hub, just a different part of the menu. And that brings us to our service called Fault Injection Service. And Fault Injection Service is our managed chaos engineering service that's then built to be able to create and run these experiments. So we're going to try one experiment on Lambda function, in this case, the application we just looked at, where we're going to add latency to our application to test what happens if each invocation takes longer, basically. We're going to run it for 10 minutes. And we go 10 minutes, and we are going to run this on 100% of invocations, meaning all invocations of the Lambda function. We're going to add 2000 milliseconds or 2 seconds. So now we are ready to start this. And obviously, to be able to do this, I'm running some load testing. So we actually have some load on my application. I'm not doing it in production. I also have dashboard. Observability is key to be able to understand what actually happens in our application. So I have this nice dashboard in place where we can follow whatever happens. And with that in place, we are ready to start our experiment. Here we go. All right, let's test it in Postman as well. We can see we're getting response, 100 milliseconds. That's cool. 132, 131, great. Now we can start our experiment. Here we go. Starting, confirming that we want to do it, because this isn't simulation. It's not just showing us what could happen. It is actually doing this fault. So it is adding latency. So beware of production environments. Now it's initiating, takes a few seconds. Now the experiment is running. So now for the next 10 minutes, it's going to add 2000 milliseconds to each invocation of my Lambda function. And as we can see straight away, testing in Postman again, the call now takes just over 2 seconds. And it is still responding. We're not getting timeouts. It's still doing what it's supposed to do. But imagine now that this is a service within a bigger application. This service gets called by some other service or by a front-end application. Now is the time to look at what impact does this have on my bigger application, the entire system. And we would do that now, testing it out, seeing what happens if there are issues. And then in the end, once we're done, we can stop the experiment or just let it finish itself. And then we learn from it. Just if this was an actual incident of some sort, we start learning from these incidents. We can do other experiments as well. We can obviously use other things than Lambda. We can do it on all sorts of AWS services. I just wanted to show one more quickly. So opening up my other template. And the template in this case is what happens if there's a fault in my API. So instead of it returning the regular 200 response, like my API should when it's working, it instead responds with a 500, meaning that something is wrong with my API. So I'll just edit the template, and we have it set to responding with, for 10 minutes, it's going to respond with 500. And let's set it instead to do it on 50% of invocations, meaning that about half of the invocations will give an error. How does my application behave then? Go, just updating the template. And then in the same way, we can start my experiment. There we go. Start the experiment. Just a bit. Still giving us 200s, which is great. It works. And now jumping over, starting the experiment. And now in the same way, this would now be as part of a bigger system. We have a front-end application. We have other services calling it. So now when we run the application or the experiment, we would then see what happens within the application when we have these 500 errors happening. So if we check once again, now we can see that call gave me a 500, so the API isn't working. Next one gives us a 200. And this is an opportunity for us to now see, do we have fallbacks in place? Do we have circuit breakers? Or how does our application handle these types of errors? So those are two examples of chaos engineering experiments we can do. Another way that we want to get customers to perhaps think about resilience is when you're in your IDE, when you're building things. And obviously, generative AI is on top of everyone's mind, so it wouldn't be a presentation without some generative AI. We have our AWS Q Developer extension for our IDE, and we can use that to get recommendations on resilience as well. And this model is trained on, obviously, all AWS documentation, all of the AWS Amazon code possible. So it has a lot of deep knowledge about how to build on AWS using best practices. So we can get recommendations from it based on my specific application. For instance, add dead letter queues or make these changes to the code or to the architecture to make the application more resilient to failure. This is something I myself is using quite a lot these days because it helps me be more resilient. I think I have 2 more minutes, right? Yeah. So one more thing. Another part of Q Developer is the more agentic way we can use it. We have an agent called Review, which can look at my application and create a review for me. So basically think of it as an AI, AI friend in the company that looks at your code and then gives you suggestions on what to improve. Here we go. So we run this agent. It reviews my code. And since I'm obviously using infrastructure as code, it's going to look at the infrastructure. It's going to look at the actual Lambda functions. And then as soon as it's done, in just a few seconds, it now gives me information. All right, in this case, we have 7 issues within my application. We have log injection in one of my Lambda functions. We are sending all of the error information into the console log. That's not great. That's something to improve. But it also tells me on the infrastructure side that we don't have object versioning on my Lambda or my S3 bucket. That's something we should have from a resilience perspective to be able to roll back and on. Gives me different suggestions in this case. So I can improve my infrastructure as code for that. Finally, have you all seen the movie Inception? Yes. So here's a bit of Inception. I talked about chaos engineering when you are building things on AWS Lambda. What's pretty cool is that the AWS Lambda service team, they are using chaos engineering as a way to improve how AWS Lambda works. So I think that chaos engineering to improve the service that you are then using, and you're using chaos engineering on. I think that's pretty cool. But they've been able to then reduce the incident response time by 90%, from 30 to under 3 minutes, which is pretty cool, with the help of using chaos engineering as a standard practice for them. All right, so with that, it's time for me to wrap up. This was a quick view at how we're looking at modern applications, some of the perhaps different failure modes that those can bring. And there's a lot of good things. You should always go fully managed if possible, but it also needs you to think about what are these different unknowns and different failure modes within that. All right, with that, thank you all very much.